Hello, this is Hugo, and in today's following 20 minutes, we're going to talk about Red Hat integration and how the AMQ component allows us to build event-driven architectures and handle distributed streaming data. So let's start with this webinar. In the past, we have been doing integration using traditional middleware, centralized type of deployments using what we used to call ESB, Enterprise Service Bus. However, with the rise of microservices, we have also seen a rise of more distributed systems that needs to go beyond the boundaries of the traditional centralized deployment pattern. So we have now the concept of hybrid cloud, where we need to go over deployments that go across different clouds, clusters, and we need to handle that type of communication using new tools, but at the same time keeping the same patterns that allows us to simplify the communication between these services. So we also noticed that there's other changes in the way that microservice architectures work. We have seen that there's storage that's now owned by the service. So we are moving away also from centralized storage. And we have also API that allows us to enable out of the context communication exposure of our services in a business fashion using traditional synchronous interactions like HTTP, REST APIs. However, when we're talking about the communication at the services layer, we notice that every time the use of asynchronous communications and decoupling between these services, it's more and more frequently. So it's important because most of the times we used to have these new greenfield architecture deployments. However, there's a lot of organizations that still need to deal with the software that is already deployed and running on the data center, where we have mainframes, databases, and legacy applications that we need to bring together with these new deployments. So there's where Red Hat integration has its major breakthrough, because we are able now to have tools that are able to create this glue layer where we can connect the traditional service deployment with the new greenfield applications. And this is mainly because agile integration, this concept that Red Hat coined a couple of years ago, it's based on three main pillars. The first one is distributed integration, where we have this lightweight partner-based integration, as well as APIs, where we have endpoints using contracts that we can then reuse to expose these services to the business. And everything running on top of containers. Everything with tools and processes that allows us to have this concept of agile integration. So when we're talking about asynchronous services communication, the idea is, instead of having point-to-point communication, that it's useful when you're just trying to link bounded context. Sometimes when these type of services explode in number and we have tons of services trying to communicate to each other, sometimes doing point-to-point communication, it's not a very good way to scale. So when we want to have high availability, high scalability, we need to decouple the services. One of the ways to decouple the services is through event-driven architecture, where we have a message bus or event bus that allows us to take ownership of the messages or the communication between the services, and then allow the next service to be able to get that information. So we get decoupling not only in the technology, but also in the runtime. So no need to share the same protocol. You can mix and match sometimes protocols, as well as you don't need to have the other service being online when you try to communicate to that. So that gives you a good advantage when you need to be sure that that you can deliver an event and somebody else will take, as well as, for example, notification patterns, where you really want to have just an event generated, but also a lot of consumers being able to listen to that event. So that's how Red Hat integration includes AMQ. AMQ is our event and message suite that allows us to get this type of communication patterns. We can do event notification. We can do also enterprise messaging, traditional GMS messaging with traditional Java broker, but also allows us to have these smaller and scale out type of architectures that allows us to have solutions that are scalable, that can grow with the amount of services, as well as being able to process streaming data. In Red Hat AMQ Suite, we have three big components. So the first one is the broker. It's traditional Java GMS broker based on ActiveMQ Artemis. That is the new version for ActiveMQ that allows us to have transactional GMS type of communication with multiple protocols and Java base. The second component is what we call the AMQ interconnect router, where we can rely on the AMQP protocol to be able to create wide distributed networks where we can just communicate services at the application layer, where we can allow to have this direct communication between end-to-end components. And finally, the third major component is MQStreams. MQStreams has it's our own Apache Kafka distribution, where the main advantage is that it has been designed from the ground up to be able to run Kubernetes, and especially being able to run on OpenShift. And this is one of the topics that we will cover more deeply in this session. Also, all these three different components are available also in Red Hat Enterprise Linux. So if you still need to run on top of the VM, the broker, the router, and the MQStreams are available on RHEL, as well as on OpenShift. So you can deploy your operators for MQStreams. You can deploy your interconnect router as the broker on OpenShift. They're all ways supported, as well as we also have this AMQ online solution that allows you to provide self-service messaging for creating and provisioning messaging infrastructure to your developers, or the developers in general, where they just see a way to request the destination, like a queue or a topic, and the infrastructure team has already created some different size pre-canned size infrastructure that is being deployed automatically without the need somebody to size and to deploy. So it's pretty useful where you just want to have a queue or a topic, try, test, and then start to be using the service. When we're talking about data streaming processing, most of the times in the old way to handle data streaming, we used to have this batch processes, or the big data lakes, where you have first provision all the information, all the data into a single repository, single storage, and then use other tools to process the information that is already stored in your data. So in this case, we're thinking about changing the paradigm to doing processing at the same time that you are receiving the data. So in this way, you can scale the way that you're doing the processing, and also you can have real-time information about what is happening while the information is coming. So you need to wait until all the information is already in the store to start analyzing that information. And there you can do different type of processing. You can do stateless processing, like just doing transformation, filtering the data, or also you can have some type of stateful processing where you can say, okay, in this certain amount of time, I want to take some information and then do relationships between the data that is flowing through your processor. And also allows us to read information from multiple streams, right? So we can get information from one source and then able to add information from other sources and then analyze both running together. And this is where MQStreams comes to in play. So MQStreams is, as I mentioned, a component from Red Hat AMQ. Everything is part of Red Hat integration. So if you have a Red Hat integration subscription, it's already available for you. And this allows us to run our distribution of Apache Kafka not only on bare metal but also on OpenShift. This MQStreams is mostly being used for traditional messaging, where we can just replace broker for topics in specific. and where you can have a scale out version of broker to deliver messages as topics. The main use case for how Kafka was designed was for a website activity tracker in LinkedIn, where we had all the different events happening in the web page being committed to a log and then being able to be analyzed after that. But also you can get some metrics, get some statistics about the metrics and collect them from different applications. So that's another use case. Stream processing is one of the most common use cases where you want to have all this information coming through in from different endpoints and then being able to process and transform those streams to then being able to deliver in another place, where you also can get the following use case, that is the data integration, where you can capture these streams and then just move data from one place to another, or you can also complement and enrich some of these data assets and being able then to do deliver of those. The last one is, for example, log aggregation, where you can just get information from one of your systems and then just append and accumulate all the different logs from the different microservices, and then have a single store where you can then take a look at them. Some of the Apache Kafka concepts that you need to be aware. The only pattern that you have, or the only semantic you can handle, is topics. So messages are sent and received from topics. Topics are just logical groupings for your messages, because the topics are itself split into what we call partitions. So the topic is sharded. So you have partitions in different nodes from the cluster, and just the topic is the logical grouping. So each one of the messages is only written in just one of the partitions. So the partitions on the way to deliver the messages through the message key. So Kafka works with a key value type of messages, and the key is used for the partition. Also, you can configure the retention of your topic. So that's one of the interesting things from Kafka, because Kafka is designed to handle and store information for a long period of time. So you can able to just deliver that information from long time ago, as well as being able to replay events. And also you can also handle replication. So in case of you lose broker from your cluster, you're able to have a replica of your data, so you can handle failures in your nodes. So the way to topics and partitions work, as mentioned, topic it's just a logical grouping. The partitions is where actually files in the file system where the where Kafka writes. So the producer gets a message, and then all the different messages that come depending on the key are stored in the partition. So in the case of message that has the key 1, all will go to partition 0. All the keys with all the messages with key 2 will go to partition 1. All the messages with the key 3 will go to partition number 2. If there's no key in the message, if you are sending a null key, then it will use a different algorithm to define to which partition to deliver that message. One important thing is the consumers. In contrast to traditional GMS brokers or traditional Java brokers, where the broker knows what's the last message that was delivered to a customer, here we're switching to a concept where we have dumb broker and intelligent clients or consumers. So the consumer needs to be aware of what's the last office that he has read from the different topics and different partitions. So all the consumer will connect and read a certain amount of partitions, and he needs to take and trace which was the last message it has read. So that's why a lot of the information now it's being delegated to the consumers or the clients. So in that way, we can increase the performance for the broker. As I mentioned, the high availability it's been achieved by having copies of the partitions. So in this case, we have 3 partitions. We have 3 brokers for the same topic. So we have what we call leaders and followers. So the one of the replicas is going to be the leader. So, and then you will have, for example, in this case, for each one of the partitions, we have 3 replicas. So we can have one replica in each one of the brokers. In case one of the brokers fails, then the next available replica will be elected as leader, so we will be able to consume from those services. As I mentioned, only the leaders are available to consume and to write information to. So the producer and consumer just connect to the leader, and that's how the messages are stored. And then Kafka, using their own internal algorithms, it's in charge of replicating the data. And everything is done at the application level. More about the Kafka components. So Apache Kafka project is a subset of elements that are part of the what we call the Kafka extended ecosystem, right? So there are a lot of other projects that are being created and managed by other third parties around the Apache Kafka components. But what we are focusing now, it's the ones that are under the Apache umbrella. So in this case, we're talking about the broker, the Apache Kafka Connect API, the Apache Kafka Streams API, the Mirrormaker, and Java clients, the clients that are available for Java. There are other clients available for different languages, but those are not a part of the Apache foundation. So we're focusing mainly on this. And we also cover Apache Zookeeper as a dependency for Apache Kafka, not for being used independently. The broker, as we mentioned, is the central component that needs to be available to receive and write messages, and this is the central component for the cluster, and it's in sync through Zookeeper that it's keeping a trace of the cluster ensemble. Kafka Connect, it's a series of frameworks and APIs to allow communication of data to the Kafka cluster and out of the Kafka cluster in the Kafka ecosystem. So they create their own framework to simply create connectors to get data from different sources and being able to put that data into Kafka, right? So you can have sink and source connectors where you can connect to different sources. The only ones that are available in the Apache Kafka ecosystem or the Apache Kafka project is the file sync, the file source. There are other connectors, but they are not available as part of the Kafka project. But you can use them and then just connect, but we are not supporting them as part of the offering. In the case of Kafka Streams, we have the streaming framework. It's also a series of APIs that allows us to read easily from Kafka and get information for streaming. So it has a DSL, a domain-specific language, so you can easily read information from Kafka and apply certain processing, like doing filters, maps, joins between topics for processing streams. So when you are playing together Kafka Streams with Kafka Connect, you can have this type of architecture where you have Kafka Connect connectors reading data from one of the systems, and then write that into a topic, and then you have applications implementing the Streams API and having processors that are taking information from one or more topics, do some type of processing. It could be just filtering or transforming the data, and the output of those services could be just be the process in the application, or you can send the information back to another topic that then it can itself become the input for another processing step. And at the end, when you have the final resource, you can either use your application to store the information, or you can use the same Kafka Connect ecosystem to then take that information out of Kafka and being able to send it back to a different system. When we're talking about replication between different Kafka clusters, we're talking about Mirrormaker. Mirrormaker is the Kafka component that allows us to send information from one data center to another in an asynchronous way. So you are able to copy and replicate information from one cluster to another. So as we mentioned, the supported components for Red Hat are the broker, Streams, Kafka Connect, Mirrormaker, and the clients for Java. That's because they're the ones that are under the Apache foundation. And those are the ones that are being delivered with the Red Hat AMQ streams. So as I mentioned, one of the values from MQStreams on OpenShift is running Kafka on OpenShift, where we have been creating this operator to deliver a way that you can have a more smooth management of your Kafka cluster on OpenShift. So it's the idea is to simplify the deployment. We are providing our own container images, following our own container registry, as well as the operators that are in charge of taking custom resources from Kubernetes and being able to transfer and deploy the different components. So for that we're using the operator pattern, where you have this desired state defined in a custom resource, and then the operator is monitoring these resource as well as the actual environment. So in the case if something is it's different, then it will apply all the different changes to make the actual environment as the desired definition that it's in the resource. And this will allow us to simplify the operations that just normally traditional humans are doing in an automated fashion. So we have several operators in Red Hat as part of Red Hat AMQ Streams. We have the Kafka operator, that is the one that is deploying the cluster, and the other operators. The user operator is in charge of managing the Kafka users. And other operator is the topic operator that allows us to handle the Kafka topics. So this is interesting value because it's going just not just deploying or installing software, but also being able to manage components when you have already deployed your cluster. And there are also operators for handling the Mirrormaker and the Kafka Connect connectors. If you need to have a key slide, this is one is where we have the different companies that are part of the AMQ suite and how are you able to use them. So you have the broker where you have durable events and you can run command queries, but it's not able to do replayable events. When you consume a message, the message is just deleted from the broker. The interconnect router allows you to do any one-to-one communication, one-to-many communications. Is based on Apache QP dispatch router. You can also feed some patterns like request response, command queries, but it's not going to be able to handle or store events or replay events. So that's one of the limitations, but it's also feasible for other patterns. The streams we mentioned is based on Apache Kafka. The best pattern is where you need to store long-term storage of events and replayable events. But if you really don't want to store information, it won't be a good pattern, and it also needs a lot of resources to start working on. And finally, MQ Online is the self-service version where you can create and deploy several of the other infrastructure components. But currently, it's only limited to broker or router, and perhaps in the future we'll be able to also provide streams capability, but it's currently not available. So in this way, you can then deploy an event managed bus where you can have input from different sources. You can use not only Kafka Connect, that is traditional ecosystem, but if we are talking about Red Hat integration, where you also have the fuse connectors, so you can mix and match fuse connectors of Apache Kafka Connect connectors to get data into the Kafka cluster. And then for the streaming application, you can use Kafka Streams API that it's embedded as part of the ecosystem, or you can then externalize the processing to another tool, like for example, Decision Manager or any other of the tools that are available, like Spark, Flink, or other type of processing. And then the results of those processings, or just from the actual cluster, you can then send them out to different storage, or you can use also the different sync connectors and fuse connectors to just send that information to other different systems or even other different Kafka clusters. Finally, one of the things that we are working now, it's Cooper. It's multi-cluster communication for Kubernetes. It's a really interesting project where we will take advantage of the interconnect router that we have for communicating service at the application layer. And with Scooper, your application could then connect to proxies in their own data center, and then using the wide MQP protocol, being able to connect to services that perhaps are implemented in different networks. So if you have seen 2 years back, Red Hat Summit, where Ted Ross, one of our engineers, present this tool during the middleware keynote, it was able to spread load from one data center to different clouds to process information. So this is a cool project. Copper.io is the webpage where you can get more information. So finally, if you need to have more information on Agile integration, you can see our ebook about Agile integration, or you can just log into our YouTube channel and see all the different videos that team has been compiled together, and get more into the different concepts for Agile integration. So thank you very much. I hope you enjoyed this session. Please join us in the conversation through Twitter, through YouTube channels, and also in the mailing list. So thank you very much for your attention, and have a nice day. Bye.